can talk about chemistry with him. Okay, so, all right, so we're going to dive back into our chapter 12 content. Okay, so chapter 12, we started on Wednesday, and it's all about alcohol. Okay, and we started talking about alcohol and how to name them. Okay, but I also wanted to give you guys a little background. I'm sure many people know that alcohols exist. But these are kind of like three of the most common, like, basic alcohols that you encounter, and I wanted to bring them up just because they're ones that we encounter like all the time in our daily life. Okay, maybe not so much methanol, but ethanol and isopropanol we definitely see all the time. Okay, so ethanol, obviously, fermentation, beverage, we've been enjoying it for thousands of years. Okay, but every once in a while you'll see in the news about people who are they get poisoned from ethanol. I just saw an article like last week about this, where people will like try to make bootleg moonshine and they'll add methanol to it because it's cheaper. But that's like deadly, poisonous. Okay, that one carbon, the difference between methanol and ethanol, is like incredibly important, in the way that the ethanol impacts your body. Okay, so it causes things like blindness, etc. So, be careful if you're into moonshine where you get it, all right? Don't let people put methanol in there. Isopropanol, almost probably every household has isopropanol in their medicine cabinet, okay? It's rubbing alcohol. It's an antiseptic, and we use it all the time, okay? So alcohols are so cool because they're really prevalent in nature and just in our everyday lives. So it's really fun to learn about this chapter because it's kind of so relevant just to our lives and the things that we use on a daily basis. Okay, so we're going to talk about the acidity of alcohols today. We've actually already discussed alcohol acidity before, back in chapter 3, because chapter 3 was all about, using acidity via pKa values and looking at the qualitative nature of acidity using the acronym ARIO. Okay, so we're just going to revisit that here in this chapter because alcohols are acidic molecules. Not strongly acidic, okay, they're not on the scale of HCl or H2SO4, sulfuric acid, but with the right base, they can definitely undergo proton transfer reactions as an acid. Okay, so just as a reminder, what does ARIO stand for? Okay, so the A is for atom. Okay, the R is for resonance. Okay, the I is for induction. And the O is for orbital. Okay, and this is from chapter 3 last semester. And this acronym is, kind of in theory supposed to help you qualitatively assess the strength of bases. And from that assessment of a base, you can kind of backtrack how acidic is the molecule. Okay, so ARIO is probably fairly useful if you don't know the pKa values. Okay, it's qualitative. It's not perfect. There's often little exceptions here or there that you encounter, and I try to bring those up when we encounter them. Okay, pKa is the quantitative method, and it's always correct. You don't have to guess. If you know the pKa's of a molecule, you can tell for sure which one's more acidic or not. Okay, so just as a reminder, where the alcohols fit in the grand scheme of things. Their pKa's are generally around 15 or so. Okay, so again, they're not very strong acids, but they can act as an acid if you have the right base. Okay, what would be a strong enough base to deprotonate them? Anything that's going to be less stable in the conjugate base form. Okay, so if you undergo proton transfer, then you make what's called an alkoxide. Okay, and the alkoxide is like the oxygen with the minus charge. Oxygen is fairly electronegative, and so because of its electronegativity, it's able to stabilize that negative charge, which is why it's a weak acid. Okay, things like nitrogen and carbon, that's what the R stands for, are less electronegative. They're less able to stabilize a negative charge, so they're going to be weaker conjugate bases, they're not going to be able to stabilize that negative charge, and so their acids will not be very strong. Wait, they're going to be stronger conjugate bases, strong bases. Okay, so we'll draw that in. These are strong bases. Okay, the N minus and the C minus. So they're strong bases, so their conjugate acid is weaker. Okay, and then the pKa scale is shown down here. So we have alcohols around 15 to 18. Okay, so the things that affect acidity of alcohols are almost always going to be things like resonance and induction, and to some extent solvation effects, which we'll talk about in a couple of slides. Okay, so when you're comparing alcohols, you don't really have to worry about atom because they're all going to have the minus charge on an oxygen atom. Okay, you only have to worry about atom if you're comparing an alcohol to a different type of molecule, like something that has a nitrogen with a proton on it, or a carbon and a proton, or a halogen and a proton. Okay, but if we're just comparing alcohols to each other, then they all have an O minus interconjugate base. So you can kind of leave the atom part off. Okay, so we're going to look at each of the factors on this slide in a couple minutes. One important thing that I want to point out is that in order for an alcohol to act as an acid, you have to use a strong enough base, which I mentioned on the last slide. Okay, and in general, that's going to be anything that's an N minus, a C minus, or an H minus. Okay, so a common base that's used to deprotonate alcohol would be NaH, sodium and hydrogen. Okay, the presence of the sodium is indicating that we have an ionic bond. Okay, so the sodium is plus, which means the hydrogen has to have a full minus charge. Okay, any counter ion like potassium, lithium, or sodium, those are all going to be +1. Okay, so they'll indicate the presence of a negative charge on the counter ion that it's with. Okay, so a hydride is a really strong base, and it'll deprotonate the alcohol to make hydrogen gas. Okay, so if we were thinking about pKa's, this one's about 15, this one's like 50-ish, okay? And if you're comparing the conjugate bases using ARIO, you can see here there's an O minus versus an H minus, and the oxygen is more electronegative, so it's more stable. Okay, so that means the equilibrium goes this way and not the other direction. The equilibrium always goes from strong acid to weak acid. It always goes from strong base to weak base. Okay, so it always goes strong reagents to weaker products. Or reactive, unstable to less reactive, more stable. Right? Any questions about the acid-base stuff that we talked about in chapter 3? This is like a very brief review, but we're going to be bringing it back here to kind of compare alcohol. So you kind of need to remember it, and we'll talk about a couple of these things, but I'm not going to go super in depth back to chapter 3. Okay, so let's take a quick look at resonance, induction, and solvation effects. Okay, so resonance and induction I stuck on the same slide because they're both kind of review topics. Okay, so how does resonance impact acidity? Okay, always whenever you have an acid-base question, draw out the conjugate base. Okay, for example, if we were to draw the conjugate base of this molecule, it would look like this. Okay, because in ARIO, what we're comparing are the conjugate bases. Okay, so we have our two conjugate bases drawn. Okay, resonance is something that we've talked about a lot this semester. Okay, and it's just going to delocalize electrons through the pi system. So the phenol becomes phenolate. Okay, and you can push the electron density on the oxygen throughout the ring, and that stabilizes it. Okay, the cyclohexanol, when deprotonated, has all of the charge concentrated on the one oxygen atom. Okay, so this is going to be a stronger base. Okay, so it's a stronger base, so I'll put strong base here, weak acid. Okay, this would be a weaker base. and a stronger acid. And that's supported by the pKa values as well. We have a pKa of 10 on the phenol. Okay, so again, that indicates a stronger acid versus a pKa of 18 for the cyclohexanol. So you could use ARIO or pKa values to assess the acidity. Okay, if you want to think about induction, induction is the pulling of electron density through the sigma bonds. It's a weaker stabilizing factor than resonance is, because resonance is actually delocalizing the pi electrons throughout multiple atoms. Induction is just kind of electronegative atoms kind of pulling the electron density towards them. Okay, it's not actually moving any electrons like we do in resonance. So induction is weaker, but still stabilizing. Okay, so an example of something that would have induction would be ethanol versus this trichloroethanol over here. Okay, the chlorine atoms are going to pull the electron density towards them. Okay, so when we draw the conjugate base of this molecule, its electrons are going to be pulled towards the chlorines, and that helps to stabilize the oxygen and the electron density somewhat. Okay, so pKa 12.2 versus 16. Okay, so you can see it's not as significant, but it's still decent of an effect. So this slide is basically reminders: what is resonance, what is induction, and how do we apply it to alcohols. Okay, the next slide is where we're going to discuss what solvation effect is. Okay, solvation effect is weaker than induction. Okay, so on the hierarchy of what's most important is below like orbital in the ARIO. Okay, so it's a very weak effect, but it can still be significant if everything else is equal. Okay, and what do I mean by that? Okay, if we look at ethanol and draw its conjugate base, and we compare it to the tert butanol and its conjugate base, if we were to go through ARIO, okay, atoms, they both have a negative charge on oxygen, neither have resonance, neither have induction, and they all are on sp3 hybridized orbitals. So we can't really use ARIO to distinguish between these two molecules. But we can tell by pKa values that one is 2 orders of magnitude more acidic. Okay, so the ethanol is more acidic. And the reason why goes into solvent effects, which we don't talk a whole lot about in sophomore organic chemistry, but solvent can play a big role in kind of the acidity of molecules. So the reason why is because anytime you have a molecule in a solvent, the solvent molecules are going to be all over and surrounding the compound that you have. Okay, so the solvent can help to stabilize the compound. It's a weak stabilization, but it's still there. Okay, so if you have an O- like we do in ethoxide and in the tert butoxide, okay, the solvent molecules can orient themselves so that electronically there are partial positive charges around that O- of the ethoxide and tert butoxide. Because the ethoxide is smaller, more solvent molecules can fit around the O-. The more solvent molecules you have around it, the more stable it is. Okay, so we have our more stable example here. Okay, because there's 1, 2, 3, 4 solvent molecules, and this is our less stable example. Okay, the tert butoxide is less stable because it's got a big bulky group on it, and so not as many solvent molecules can fit around the O-, which means it's less stabilized. Okay, so a more stable conjugate base results in a stronger acid, so that's why the ethanol is slightly more acidic than the tert butanol is. Okay, so this is a solvation effects are something that you would look to when everything else is equal to explain the electronegativity, or not the electronegativity, the acidity difference. All right, so we're going to practice with a question just to kind of drive all of this home. Okay, so there's 4 different molecules on this slide, and I want you guys to kind of rank them in order of decreasing acidity. So most acidic on the left, least acidic on the right. So go ahead and give it a shot. Good. And then the code, I wrote it on my phone. Give me a second. It's 596893.
Imagine your hair straightened.
Your hair is getting long. It's gone.
It used to be so much longer. Is she dead?
You gonna cut it?
She did. Like short.
What? Half short. Ungrateful. You heard
So
me.
I can grow it. Grow it healthy and strong. Look what my hair used to be.
Do you have gum?
Mm-hmm.
Yeah, right here.
It's like,
I'll give you guys about 10 more
That's fine.
seconds.
you want it?
Yes, please.
Oh, okay. You know, Megan woke me up at 8:22 and said, it's time for ochem. And I ran.
Where's the picture?
Bro, I don't know why, but this picture had me weak last night. Christian.
All right, is everybody clicked in? We're going to go forward. Well, there's only one response in that one. Let's see.
My nose wrong. Could you imagine?
Do you guys want to just click in real fast? Again, real fast. I'm sorry, my clicker program is really crazy. It's because I had to switch because of Duo. I blame Duo for this. All right, so most people did go with B. That's good. Okay, so actually B is the answer. But let's talk about why. Okay, first off, anytime you have a question like this, again, draw out all the conjugate bases. Okay, don't just try to eyeball it. So let's draw them out. I'm going to choose the picture color besides pink because pink's hard to see. All right, so we're going to draw our conjugate bases. Molecule D is my favorite because it looks like a turkey from Thanksgiving. Okay, so if we're thinking about Oreo, okay, atom's not a factor here because they all have an O minus. So let's move on to resonance. Do any of the molecules have resonance? What do you guys think? Yeah, which one? B. B has resonance. Okay, we have a Lilith lone pair. We can draw a resonance contributor for this molecule. And nitrogen will end up with not a minus, a lone pair, like so, and we'll get this guy. Okay, so there's a resonance contributor for B. B is the only one with resonance. Some people might think that A has resonance, okay, but it does not because there's an sp3 hybridized atom right here. Okay, so be careful with A. So B has to be the most stable because it's the only one that has resonance. So we cross off A and we cross off C. Okay, so after B, A is the next most stable. Okay, A is the next most stable because it's got some induction via the oxygen atom over here. Excuse me. So the oxygen can help pull electron density towards it through the sigma bonds. Okay, next is between C and D. C is smaller, less steric hindrance than D. Okay, so if you're thinking about solvation, you would have like a lot more solvent molecules around C than you would D because D's turkey-like nature makes it so that the solvent molecules can't get close to that oxygen. Okay, so C is more stable than D because of solvation. Any questions at all about this? All right, good. Acidity is easy peasy then. Let's move on to thinking about how we make alcohols. Okay, so again, every time we encounter a new functional group, We're going to spend time talking about how to name it. We're going to spend time talking about its properties. And then we move on to how do we make that new functional group. Okay, so that's kind of the stage we're in right now of this chapter. How do we make alcohols? And luckily, we've talked about a ton of ways to make alcohols already. Okay, so this slide and the next slide are going to be very heavy on review, first semester topics. Right? So again, this is kind of one of the reasons why chapter 12 is a little hard, because we bring back a lot of stuff. Okay, so one way that you can make alcohols is via substitution, and just straight up like SN1, SN2. Okay, in general, we're either going to be reacting a tertiary alkyl halide with a weak nucleophile, such as water, to make an alcohol. Okay, so this is going to result in an SN1 process. Okay, so you do have to some extent know, is the nucleophile weak or strong? Okay, this one up here is a strong reagent. The one on the bottom is weak. How do you know? This one has a minus charge, this one's neutral. Okay, this is a tertiary alkyl halide, this is a primary alkyl halide. Okay, the SN1 mechanism will have a carbocation intermediate. Okay, so remember SN1 is susceptible to carbocation rearrangements. Right, and if we take a tertiary alcohol, that'll make a very stable carbocation, and then we bring in a weak water molecule to create the alcohol. For SN1, it's not going to be very practical to use primary or secondary substrates. They'll react too slowly. Okay, remember the rate is dependent only on the nucleophile. The nucleophile is pretty weak to start with. Bringing in a less stable carbocation would result in a very large activation barrier, which would be slow. Okay, so we're not going to, let me redraw that. The rate is not dependent on the nucleophile. The rate is dependent on the substrate. Rate equals K times substrate for SN1. Okay, so the rate is only dependent on the substrate. That's why it's slow if you have primary or secondary. Okay, so the rate for SN1 is dependent on the substrate. So if it's primary or secondary, it'll be really slow because of the big activation barrier. Okay, the rate for SN2 is dependent on the nucleophile. Rate is equal to K times nucleophile and substrate. That's why it's a bimolecular process. I can feel my face turning red because I made a mistake. It's embarrassing. I'm sorry. But yes, so SN2 is dependent on the nucleophile and the substrate. Okay, so again, some review that I need to just like think through before I say things. Alright, the SN2 is going to be facilitated by a strong nucleophile, something with a minus charge. And if we're trying to make an alcohol, it needs to be an OH minus. Okay? Also, primary substrates will be the fastest because you have to have nucleophilic attack. So if it's secondary or tertiary, that'll be too much steric hindrance. Okay, so it would slow the reaction down. So sterically unhindered substrate, strong nucleophile for SN2. For SN1, stable carbocation and weak reagent. And again, secondary substrates aren't going to be effective for SN1 because it would be too slow. And then for SN2, if you have like a secondary or tertiary substrate, that would actually favor elimination. So you get byproducts that you don't want. All right, any questions about kind of this substitution review? I'm not really going to be like super tricky with like substitution and elimination and things like that, like we were last semester, because last semester we were trying to determine, you know, do you understand substitution and elimination? Now we're trying to determine, can you make alcohols using substitutions? That's kind of the more key factor. Yeah.
Secondary substrate complex, never mind.
Yeah. Any other questions?
Well,
Yeah.
so who was secondary on like an exam, like in the place with no reaction that you broke into?
Let's see. If you had a secondary secondary substrate on an exam, there might be like, maybe it would be a conceptual question where you would have to realize that it would be too slow with SN1, or the SN2 would favor elimination. So you might have to know that like the major product would be elimination product and the substitution would be a minor product. So like reaction would happen, it's just not the one we want. Okay, one more review slide. Okay, so the other ways that we learned how to make alcohols were using addition reactions. And we learned 3 ways to do this in chapter 8 with an alkene starting material. Okay, so we'll briefly review them here on this slide. Okay, the first way was using acid catalyzed hydration. Right, and the acid catalyzed hydration went through a carbocation intermediate. Okay, and we got a racemic mixture of products. Okay, so that's kind of like the stereochemistry. And it was Markovnikov addition. Okay, so it adds the more substituted carbon atom because of that carbocation intermediate. Okay, this one also susceptible to rearrangement. So, like that, rearrangement instead of the carbocation. Okay, the second reaction was oxymercuration, demercuration. Okay, this one resulted in anti-stereochemistry. All right, and Markovnikov regiochemistry. All right, so we're going to add the more substituted of the 2 atoms. And this reaction was better than acid catalyzed hydration because it was not susceptible to rearrangement. Because there's no carbocation intermediate. Okay, our intermediate in this reaction looks like a cyclic molecule. Okay, we had that oxymercurium ion. So it looks like this right here. Okay, and then the last reaction was a reaction we learned about that had anti-Markovnikov regiochemistry. So that's why it was really important, because it was one of the few ones that we had that would add to the less substituted carbon. And the reason for this is because of the kind of electronic and steric effects of the reaction. This one was concerted, so there wasn't an intermediate. Right, and it gave us syn addition, or syn stereochemistry. Okay, so what do you need to know? Pretty much like the regiochemistry and stereochemistry, so that you can predict the product. Okay, that's the main way that we're going to use these reactions in chapter 12 to make alcohols. So to accurately make alcohols, you need to know the regiochemistry and stereochemistry of the products that would form from these reactions. You also need to remember the reagents and which reagents will bring about these transformations. Okay, we're not going to be like super crazy and like give you, you know, weird reagents that you've never seen before and ask you, you know, which reagent is the right one. You know, like I wouldn't give you like BH3 THF versus like BH4 THF, like doesn't make any sense. But you know, I would expect you to know in a synthesis, is it better to use the oxymercuration demercuration, or should you use the hydroboration oxidation reaction? Okay, so you need to be able to manipulate them based on their regiochemistry and stereochemistry. All right, any questions about these review reactions from chapter 8? Yeah.
What's
Anti-stereochemistry means that like the hydrogen has to be on the opposite face compared to the oxygen that you add. Okay, so like a wedge and a dash versus syn addition where they're on the same face when they add. This would be syn and this would be anti. Any other questions? Okay, the next thing we're going to do is we're going to look at new ways to make alcohols. Okay, so the new way that we're going to learn how to make alcohols is via reduction. Okay, we've talked about reduction a little bit this semester. Okay, it's come up when we've converted nitro groups to amines in chapter 18. Okay, we did that with the zinc, mercury, HCl reagent. You have a
I do have a question.
Oh, okay.
For the racemic mixture one,
Uh-huh.
what would you say comes to that?
Okay, so for the last slide, if you have a racemic mixture, then you get both the R and the S, for example, if you make both. Yeah. So reduction, again, we've talked about nitro to amine. We've also used reduction when we did the acylation reaction and converted that acyl group into an alkyl group. Also in chapter 18 for that Friedel-Crafts acylation reaction. Okay, so reductions are something that we've been talking about a little bit. And we're going to continue to use reduction to our advantage here to make alcohols. The reagents we use are going to be different though. So instead of using like zinc HCl, we're going to use some new reagents that you guys have never seen before. So that's why we're going to talk about them. This slide is just a reminder about what it means in organic chemistry for a reduction to occur or for an oxidation to occur. Okay, so in organic chemistry, a reduction is when you decrease the number of carbon to electronegative atom bonds. Okay, for example, this molecule on the left, acetone, has 2 carbon to oxygen bonds. Okay, the reduction occurs, now we only have 1 carbon to oxygen bond. So we've reduced the number of carbon to electronegative atom bonds. Okay, you can also think of a reduction as adding the number, like adding new carbon to hydrogen bonds. Okay, so in this molecule there's 0 carbon to hydrogen bonds, and in this one there's 1 carbon to hydrogen bond. The hydrogen's not drawn in, but it's right there. Okay, so you can think of a reduction as either case. The oxidation is the exact opposite. So the oxidation would be going from here to here. Okay, so oxidation is increasing the number of carbon to electronegative atom bonds, okay, and decreasing the number of carbon to hydrogen bonds. So just kind of a broad way to tell, is this an oxidation, is this a reduction? You're always going to be looking at how many carbon to oxygen bonds are in the starting material to the product, or how many carbon to hydrogen bonds do you have versus starting material to product. Okay, so there's kind of 3 different reagents we can use for reducing this carbonyl bond, a carbon to oxygen, into a carbon to alcohol. Okay, and the 2 reagents are very similar to each other, the first 2. Okay, they work in the same way, so I'll say they're very similar. Okay, in their mechanism. So very similar in mechanism, how they work. So that's nice. Okay, the one thing to keep in mind is that LAH is more reactive. Okay, and that's important because it'll react with more molecules, different types of functional groups compared to the sodium borohydride. So the sodium borohydride is mild. Okay, and the last reagent up here, hydrogenation with the metal catalyst, that's again a review reaction from chapter 8. Okay, so from chapter 8. Okay, but we're going to be using it to kind of just compare to these new methods. Okay, so we'll go through and look at the 2 new reagents, sodium borohydride and lithium aluminum hydride, and then we'll compare them to hydrogenation. Okay, so sodium borohydride is NaBH4. And if you want to look at it drawn out right there, it's a boron atom that has 4 hydrogen atoms. Okay, so the boron has a minus charge overall, and then the sodium's just the counter ion. Okay, what the sodium borohydride essentially is it's like having an H minus. Right, so normally H minus is a strong base, which we don't want to have happen here. If we want to reduce the carbonyl and convert it into an alcohol, we want the H minus to act as a nucleophile. So the key thing that using sodium borohydride does, the boron with the 4 hydrogens versus an H minus by itself is it allows the H minus to act as a nucleophile, okay, instead of as a base. So it's called a delivery agent for the hydride, okay, so we have a nucleophile and not a base. So it basically changes the function of the H minus, okay, but the main idea is that it's delivering essentially like an H minus to the molecule. Okay, so the overall conversion is shown up here. We go from a C to O bond to a C to OH bond, and that's not like the prettiest looking bond I've ever seen. Trying to move your button here. That's not prettier at all. What I did. Okay, there we go. An H. So there's basically like the addition of two H's to the molecule. Okay, so also of note, the solvent up here. Okay, note the solvent can be protic, okay, which means they have the capability to hydrogen bond. Okay, so that's one thing that's nice. You can do this reaction in water. Okay, you can be green if you want. Green chemistry, not like the color. All right, so how does it work? Okay, the mechanism is actually very straightforward. I will say that the Klein textbook that we use oversimplifies the mechanism. So I'm going to teach it this kind of like simplified way, but know that in reality it's a little bit more complex. In reality, the sodium atom has a role to play, you know, and it's not really this straightforward. But essentially, like the main ideas are conveyed in the mechanism that Klein uses. So that's what we're going to go with. You guys don't need to worry about the complex parts. So the way it works is number one, nucleophilic attack. You have your essentially H minus coming in and attacking the carbon of the carbonyl. This is going to be a huge kind of motif or theme in the rest of this semester. Okay, that electrophilic carbon atom getting attacked. Okay, so this reaction will come up later in chapter 19. Okay, so don't forget this reaction after midterm 2. We're still going to use it. Yeah. That's a good question. I'll get to it. The LAH, because it's more reactive, might be a little bit more like detrimental. Say the molecule has multiple functional groups, and we only want to react with one functional group, and not like all of them. So the LAH might react with all of the functional groups on the molecule. The sodium borohydride would only react with kind of the more electrophilic ones. So I'll talk a little bit more about that in a couple slides. Okay, so this milder reagent is useful because it only reacts with aldehydes and ketones. Okay, so only reacting with aldehydes and ketones is significant because, like I just mentioned, if you have, say, other functional groups present, the sodium borohydride is only going to react with the aldehydes and the ketones and not the other functional groups like esters or carboxylic acids that have carbonyl groups as well. Okay, so the first step is nucleophilic attack. When that happens, the result is a new carbon to hydrogen bond, okay, and we make an O minus. Okay, this is called a tetrahedral intermediate. Okay, because we've converted an sp2 hybridized atom into an sp3 hybridized atom. Okay, and then the last step is basically a neutralization step. It's a proton transfer. And this is where that protic solvent comes in to help us out. We have water or methanol or ethanol, whichever solvent you're using that has a proton to give up. We'll give up a proton to this O minus, and we'll end up with a neutral product. Okay, so our end product is going to be an alcohol. Okay, if you reacted this with an aldehyde, okay, your end product would be a primary alcohol. So you would get, I know that's hard to see. Let me see if I can draw it somewhere else. Where could I draw it? Up here. So say we had an aldehyde, when we did this reaction, we would add one hydrogen, and there'd already be a hydrogen there. So an aldehyde would result in a primary alcohol, okay, while the ketone results in a secondary alcohol. Okay, so depending on the starting material that you use, you can make different types of alcohols. Okay, so it's a pretty straightforward reaction that gives us lots of different ways of making alcohols, primary and secondary. Okay, how does LAH work? Pretty much exactly the same way if you have a ketone or an aldehyde. Okay, so if you start off with a ketone, your LAH comes in, acts as a hydride delivery agent. Okay, again, same exact mechanistic steps, nucleophilic attack on that electrophilic carbon atom. Okay, we get our tetrahedral intermediate. Here's the new carbon to hydrogen bond. And then the last step is proton transfer to neutralize. Okay, so LAH works the exact same way. So no difference here in how they function. The only key difference is what I'll talk about on the next slide, and that's going to be to show you how LH is more reactive than the sodium borohydride. Also notice, again, if you start with a ketone here, you end up with a secondary alcohol. Up here, we start with an aldehyde, and we end with a primary alcohol. Okay, because the aldehyde already has one hydrogen on it, whereas the ketone has one R group. So this slide is going to explain kind of like the reactivity, the extra reactivity that LAH has. So as a reminder, I'm going to write up here, LAH is more reactive. And what that means is that the LAH is going to react with more functional groups than the sodium borohydride would. Okay, so sodium borohydride will only react with ketones and aldehydes. Okay, but LAH will react with carboxylic acids and esters as well. Okay, so it's going to react with lots of different types of molecules compared to the sodium borohydride. One thing I also want to point out here that I didn't point out on the last slide is that the LAH has two steps incorporated into it. Okay, notice that the LAH is not kind of like in solution with a protic solvent like our sodium borohydride was. The LAH is kind of like a two-step reaction. We have a 1 drawn up, that means the LAH is added first. The reaction is allowed to proceed. After the LAH has reacted, then we add water in a second step. The reason for this is, again, because LAH is very reactive. If you add water in with the LAH together, the LAH and the water will react together instead of reacting with the carbonyl bond that you have. So it's really important with LAH to add water second as a separate step. They can't go in together. Again, this is because LAH is more reactive. Okay, so a two-step reaction. If we want the LAH to react with a carboxylic acid or an ester, then we need excess LAH, okay? Or it might say 2 equivalents. Okay, the reason for this has to do with the mechanism. So let's take a look. Why do we need 2 equivalents or excess LAH? Okay, the first step is just like we've talked about, nucleophilic attack. So here's your hydride delivery agent attacking the electrophilic carbon. Okay, we get our tetrahedral intermediate. And this is where we do something that we've never really done before. Okay, here in this intermediate, what we're going to do is we're going to kick off an O- as a leading group. Okay, so we use this molecule as our leading group here. Normally we don't do that. Normally we say O- is a poor leading group. It's not very stable. Okay, and the reason why we can do it here, but we didn't really do it ever before, is because this intermediate is very high in energy. Okay, so kicking off the methoxy group actually makes it more stable. Okay, so it's going to stabilize the molecule by losing the methoxy group. Okay, so forming the carbon to oxygen pi bond is stabilizing. So our second step is loss of a leading group. And then we have carboxylic acid or ester. Okay, notice the product we make. We make an aldehyde. From the last slide, we know that aldehydes will react with LAH. Okay, so that's why a second equivalent is needed. needed. Okay, so we have one equivalent here, so this is the first equivalent, and right here is the second equivalent of LAH coming in, and it's going to attack the aldehyde that we make as our intermediate. So the last two steps are the same from the previous slide, nucleophilic attack and proton transfer to neutralize. So overall, we've added 2 carbon to hydrogen bonds through this mechanism. Okay, here's the first carbon to hydrogen that we added, and here's the second carbon to hydrogen that we added. So we brought the hydride delivery agent in twice. We added 2 hydrogens to that carbonyl carbon, and the result is an alcohol. Okay, both of these reactions make primary alcohols. Also note, with the ester, you get a byproduct. Okay, whatever you kicked off as your leading group. All right, any questions at all? Okay, this is also a mechanism that we're going to revisit later this semester in chapter 20. It's going to come back. So I have a summary slide. Here are the 3 methods that we talked about that can reduce. I didn't specifically go back and look very detailed at the hydrogenation, but the hydrogenation works the exact same way we've talked about. Okay, the big thing about the hydrogenation reaction is that it is not selective. Okay, so hydrogenation will add hydrogen atoms to every pi bond in the molecule. Okay, so not only the carbonyl, but also any pi bonds that are hanging out. Okay, so hydrogenation is something that you would use only if you wanted to get rid of all pi bonds. Okay, or in theory you could use it if you only had a carbonyl and no other pi bonds. Okay, but it's not a selective reagent. The reason why using the hydride delivery agents is helpful is because they are selective for the carbonyl. Okay, so these ones are the selective. So I'll say selective for C double bond O. Okay, so both of them will convert a ketone or aldehyde into an alcohol. Okay, and then remember that the lithium aluminum hydride is more reactive and has to be added in 2 steps. Okay, with water as a second step. Okay, so these are kind of like the 3 reduction reactions that add hydrogens to the carbon to oxygen bond, and you just kind of need to know, when would you use which one, basically. Hydrogenation will work, but it's not selective. Okay, LAH can reduce aldehydes, ketones, esters, and carboxylic acid, so it's very reactive. The sodium borohydride is mild and will react with aldehydes and ketones only. Okay, lastly, you could substitute the boron or aluminum reagents with lots of different types of substituents. Okay, so adding different substituents to these molecules would vary the selectivity and reactivity. Okay, so you can maybe make the borohydride reagent more reactive or even less reactive depending on what you add to it. Okay, so there's lots of ways to kind of tune these reagents. We won't really talk a whole lot about these in class. There's one reaction we do talk about later this semester where we kind of tune one of these reagents, but I just wanted to make you guys aware that there's lots of ways to kind of manipulate these reagents even more. All right, I'm going to give you guys a little homework. Okay, what I want you to do for Monday is come in on Monday morning with answers to these 2 practice questions.